So what we're going to look at today is graphing. Graphing sine, graphing cosine, graphing tangent. And in order to get a graph, what we're going to look at is a little unit circle program that I've made here. First of all, this is in Geogebra. Geogebra is free to download. You can create all sorts of your own applets and graphics and try graphing different things. So if you want this for your computer at home, it's quite nice. So if we're thinking about sine and cos, and what I've done here is I've got a little unit circle. And sine is our y-coordinate. So I've got a point on our unit circle. And what I'm going to do is I'm going to rotate this point around from 0 to 2 pi. So I'm going to rotate it around from 0 to 2 pi. And as I rotate it, I'm going to keep track of the y value, because that's my sine. And as I keep track of it, I'm going to draw a graph as we go along. So if I grab a hold of this point, can you see that right at the beginning, our y-coordinate is 0. But as I drag it around, when I get to pi over 2, my y-coordinate is 1. And I go past and starts going back down again. At pi, the y-coordinate is 0. Pi over 2, it's at -1. And then back to 2 pi. And then if I would keep going, it keeps repeating itself. So if we wanted to continue this, we could. So from the sine graph, we can see a couple of important things. We can see that it goes up to 1 as the highest value, and down to -1 as the lowest value. So our range goes from -1 to 1. We can see that in quadrant 1, from 0 to pi over 2, and in quadrant 2, from pi over 2 to pi, it's positive, which according to the cast rule is correct, right? But then in quadrant 3 and quadrant 4, it's negative. So this makes our sine graph. If we wanted to see our cosine graph is the x-coordinate on our unit circle. At 0, our x-coordinate is 1. So our cos graph starts up here at 1. And as we go around, it has the same kind of shape as our sine graph, but it's just shifted over. So you can see for cos is positive in quadrant 1, negative in quadrants 2 and 3, and then positive again in quadrant 4. So that's where we're going to start. What you need to be able to do is draw your sine and your cos graph from 0 to 2 pi or from 0 to 360 degrees. These are your parent graphs. So I'll get you to draw these on the side of the page of page 514. The blue one is sine. The important thing is that you show it goes up to 1 and down to -1. And then along the x-axis, go from 0 to 2 pi and split it up into 4 like you're splitting it up into 4 quadrants. And your 4 quadrants go from 0 to pi over 2 to pi, pi to 3 pi over 2, and 3 pi over 2 to 2 pi. So take away sine and cos this time, and we're going to look at tan. Now on the unit circle here, tan is represented by the green line. And I know you probably can't see it too well, some of those colors, but if you draw a point on the unit circle and you actually draw a tangent line at that point, the length of the tangent line from the point back to the x-axis is the same as the tangent value. So this is what the tangent graph looks like as we go around. First of all, it starts at 0. And then can you see that that green line is getting longer and longer and longer and longer and longer until you get to 90 degrees, at which case tan is undefined. And so it kind of looks like an x cubed graph repeated over and over again. It's a little bit different shape than that. But if we're graphing tan, it has asymptotes wherever you have pi over 2 or 3 pi over 2. And it kind of looks like x cubed graphs in between. So I'll let you graph that one down on that page as well. Okay. So some important properties and some highlighting to do in your notes now. So we call any kind of function that repeats itself over a certain period of time a periodic function. And how long it takes to repeat itself, we call it the period of the function. So when you have this graph, and this is the graph of sine x, the period is 2 pi. Because every time you go 2 pi, it's going to repeat itself and be at the same place. And that makes sense because of coterminal angles. If you go around the circle, you're going to end at the same place again on the circle if you add 2 pi. So the domain of our function is everything, because it keeps on going forever. And we have arrowheads that we should draw on the end to show that this pattern keeps continuing as we go along. The zeros, the x-intercepts, are equal to wherever we have 0, pi, 2 pi, 3 pi. So we have to be able to write all of these down, and the way that we write them all down is in this general form where it's k times pi. Because you got 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, and you have the negative ones as well. So anytime that k is an integer times by pi, you're going to get a 0 or an x-intercept. It has a maximum value of 1 and a minimum value of negative 1, so the range goes from negative 1 to 1. You can also write this in interval notation with square brackets because it includes negative 1 and it includes 1. Some other important definitions. The amplitude of a sinusoidal function is the distance from the middle of the graph, and the middle of the graph, this center line, is sometimes called the sinusoidal axis or the average. So if this was a graph about temperature, because temperature is somewhat periodic, because in winter it's generally cold, and summer it's generally warm. It doesn't work out perfectly. By the way, I looked at Environment Canada, it's supposed to be plus 10 on Sunday. But we'll see if that actually happens. Anyways, so the middle is your average. And the distance from that middle line to a maximum or to a minimum is your amplitude. Amplitude is always a positive value. You can also find your amplitude by taking your maximum plus your minimum and divide it by 2. Well, not the maximum minus your minimum. Sorry. Because that's how. Because once we find the distance between our maximum and our minimum, that's going to be double our amplitude. And dividing it by 2 will tell us what our amplitude is. So we have a lot of the same kind of things happen with our cosine function. Our amplitude is still 1. Our period is still 2 pi. So there's our amplitude of 1. Our period is still 2 pi. Our domain is still everything because this pattern continues on forever. But now how are we going to write the zeros of the function now? Because if we think about where cos is equal to 0, cos is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and could be positive or negative. So we see that it's always over 2, right? Now how are we going to write the top? Because if we write k pi over 2 and say k is an integer, what happens when k is equal to 2? Then you just have pi, but pi isn't one of them. So we have to figure out how are we going to write this down. Okay? How do we write 1, 3, 5, 7, all of those ones? And I'm going to show you two different ways that we can write this down. We can't do this odd k pi. That's not mathematical, but it's the right idea. Can you see that they're all odd numbers? But we can't write odd k pi. It sounds pretty cool, but it doesn't work. So how do we write an odd number? How do we guarantee that we have an odd number here? 2k plus 1. Because if you multiply any integer by 2, you're guaranteed to get an even number. Then if you add 1, you're guaranteed to get an odd number. So one way we can write the zeros is a fraction like this, 2k plus 1 times pi over 2, because this is an odd number times pi over 2, where k is an integer. The other thing to notice, and another way of writing this, is as follows. Here we have pi over 2. There's our first one. How far is it till we get to our next one? How much do we have to travel to get to the next time it's equal to 0? Think about your unit circle. Where is it equal to 0? It's equal to 0 right at pi over 2. How far do you have to travel till it's a 0 again? Down to 3 pi over 2, you're having to go plus pi. And then you'd have to go plus pi again, plus pi again. So another way of writing the same thing is to start with one of your zeros. One of my zeros is pi over 2. Then I can add or subtract pi as many times as I want to get all the other ones. So if I have pi over 2 plus k pi, where k is an integer, because then that would include the subtracting, that's another way to say all the zeros. Now I got this pi over 2 plus k pi by thinking about how the graph worked and how there was a difference of pi in between each one. You could also take this equation that we did in blue first, multiply it out and simplify it, and you would get the same thing. So there's two different ways you can state all the zeros for cos. Whichever one you feel makes the most sense for you is going to help you the most. So one of them is odd numbers of pi over 2. The other one is starting with pi over 2 and adding pi or subtracting pi as many times as you want. Again, we have a maximum of 1 and minimum of 1, and the range, the same, goes from -1 to 1. Sine and cosine are the most common graphs. We don't do as much with tan, but if we did stuff with tan, if we look at our tan graph doesn't have an amplitude because it doesn't have a maximum and a minimum. Okay? Our tan graph does have a period. If you look at your graph, how long does it take to repeat a tan graph? Only pi. So that's one of the differences between our sine and cos have a period of 2 pi. Our tan graph only has a period of pi. The domain of our tan graph is not a pretty thing because you have all those asymptotes. So the way that you write your domain for your tan graph is you say it's all values of x except x can't equal, well, what can't it equal? It can't equal all of the zeros of cos. Does that make sense? Since tan, big idea, is what over what? Sine over cos. Wherever cos is 0, you're going to be dividing by 0, and that's not allowed. And so that's why we get all those asymptotes at the same place where cos is equal to 0. And so we can say our domain is everything except x can't equal, and then you get to choose one of the two ways of saying your zeros from cos that we just did. For example, you could say it can't equal pi over 2 plus k pi, where k is an integer. But everything else is fine. The range of tan is everything. And your zeros or x-intercepts of tan are going to be exactly the same as sine. Because if you have a fraction, the only time a fraction is equal to 0 is if your numerator is equal to 0. And since tan is sine over cos, where tan is equal to 0 is going to be exactly the same place where sine is equal to 0. And we know our zeros from sine were this. So there we have a little bit of an introduction of the properties of sine and cosine and tan. Last thing that you can highlight is the definition of amplitude. Even though we've already talked about it, that's on page 515.